semester, and then I'm going to cover the metallization and the problems and solutions is going to be the main topic of today's lecture. Okay, we have discussed that the metallization it consists of many complicated layers, like silicide layers and diffusion barriers, and even with the metal itself, we have to do something for the metal itself. Now, the problems that we are going to have with the metallization is, or you may say, the problems that we have to overcome to VLSI possible in the industry are the junction spiking, and extrusion, or the whisker formation in a hillock. These two phenomena is a little bit different in nature. And then corrosion, and most importantly, we are going to talk about the electromigrations. Migration. And finally, we are going to solve more migration. So the first topic, junction spiking, is what you can see here is that if you use a pure aluminum as a metallization lines, and then the silicon contact here, the aluminum is going to out diffuse into silicon, or the silicon atom is going to be out diffused into the aluminum to form these spikes. You know, in the silicon surface there is not uniform at all. So randomly it's going to have some weak spots where the diffusion process can happen easily, okay? And then with this spiking, it grows very fast, even at low temperature. This is actually the experimental results, and then see after 5 minutes, I think it's about, the temperature is about 500 degrees centigrade or so. 450, oh yeah, it says 450 here, right? The temperature is 450 there. And then within 5 minutes, you're going to see this is a junction depth, okay? You make junctions. You make source and drains on the silicon substrate. And then after 5 minutes, just the silicon goes deep into the silicon substrate, penetrating the junctions. So if this happens, then the input that we apply to this aluminum metal line should be limited inside these junctions, inside the source and drains, but it's going to go directly input to the silicon substrate. Okay, so that's going to give us a problems in the performance. And this is very fast. And the reason why the silicon can diffuse into the silicon, the aluminum can diffuse into the silicon substrate, or the silicon can diffuse into the aluminum lines, it's the same phenomenon. Okay, moving aluminum into silicon, or the silicon moving into aluminum, is the same phenomenon. And if you look into the phase diagram of this, okay, this is the aluminum and silicon phase diagram, and here the aluminum 100%, okay? And then if you look at this region, the solubility limit, solid solubility limit, you can see up to 1.659 or 1.65% can be soluble. Silicon can be soluble into the aluminum. Okay? So how can you prevent this? You just put the silicon in the aluminum metal lines beforehand. Okay? And then it already has a solubility limit of silicon into aluminum so that no more silicon diffusion into aluminum can happen. That's how we can prevent the junction spiking. Okay? So to prevent the junction spiking, all we have to do is we are going to add some 0.16% of silicon into aluminum lines. And then we can prevent the junction spiking, right? And the extrusion and whisker, basically it happens due to the stress. Here is a list of linear expansion coefficients. And you can see the aluminum is 25 times 10 to the 6. But you see the silicon 2.5, silicon oxide 0.5. So there's an enormous difference in the linear expansion coefficient, which means if you do the thermal cycles, then the metal lines which is deposited on top of the silicon will expand. The metal lines will expand while the silicon substrate is not, so that we are going to have a mechanical stress. And this mechanical stress will lead us to have the abnormally fast growth of a single crystal, and that is going to be called whisker. Okay? And sometimes we are going to see some kind of rocks on top of the film. And this is actually the scanning electron microscope of extrusions on a thin indium film after this is sputtering. Okay? And you can see the extrusion of the indiums in some weak spots like that. And this come from the mechanical stress. Okay? Due to the difference in the thermal expansion coefficients between the silicon substrate and the metal lines. This whisker will give you short. Okay? Let's suppose you have a metal line, something like this. It's aligned with something like this. And then if whisker grow and some part of this metal lines, and you're going to touch the next nearest metal lines, and then these two metal lines are going to give us a short. Okay, so this whisker is not a trivial problem. And extrusions, we are going to have a rough surface, and that rough surface is a big problem in the lithography. In the lithography, we are going to have very fine patterns. So extrusion and whisker, it come from the mechanical stress, and it's not a trivial question at all. We have to prevent this. Now, how can you prevent that? We are going to add the vacancy binder. Where is the vacancy binder? Let's cover the HELOC. HELOC is if you have a grain boundaries in the metal lines, okay? And then you have a triple points like this, and if the metal atoms can travel along this grain boundaries much faster than intergrains, because this grain boundary is the place where the atoms are not arranged regularly. So it's not compact. So the metal atoms, usually impurities or whatever, it is going to move, travel fast, migrate fast along the grain boundaries. And if you have a triple points like this, and the metal atoms is moving from here to go to these two places, then you're going to have a depletion of metal atoms, because you have two exits where you have just one entrance. But if you have if you have a situation the other way around, in other words, the atoms is moving along these two directions and then has one exit, then you are going to have accumulation of atoms at this triple point, and then you're going to have a huge rocks in there, and we call that the hillock. Okay, and this hillock is really bad in the lithography, as you can see here. This is the metal lines running different heights of the substrate, and then if you form a hillock on the metal lines, then you're going to have a very rough surface, and it is really hard to focus in the lithography, because we are talking about the micron size lithography, right? So extrusion, whisker, that is coming from the mechanical stress, and the hillock, that is coming from the grain size and grain boundary stuff, okay, in the metal lines. And those three, extrusion, whisker, hillock, are related with the diffusion of atoms. So to prevent this, we're going to add the vacancy binders. Okay, vacancy binder, which means it is going to make the metal atoms heavy. Okay, this metal atoms has to diffuse with the coupling of the vacancies, and if you slow down the mobility of the vacancies, it means that the atoms cannot move fast, right? So what are the elements for the vacancy binders? Tin, cadmium, indium, and typically we are going to add a very little amount of these atoms. We are not going to, in a junction spiking case, the silicon, we should not form the precipitation. Precipitation means we have to add the silicon below the solubility limit, right? Solubility limit. If you add these things beyond the solubility limit, then you're going to have a precipitation, and this precipitation, and these precipitations will not going to work to prevent the junction spiking anymore once it forms a precipitation. Likewise, if you add the vacancy binders beyond the solubility limit in the silicon and the aluminum, then these vacancy binders will not going to work as a vacancy binders. So we have to add these vacancy binders less than the amount for the solubility limit. Okay? And the corrosion, aluminum, only chlorine with moisture is going to corrode the aluminum. The others, the aluminum is not going to be corroded, okay? But it is important because if you look into this, this is a pad actually, and this line is a pad, and then you have a gold wire there, and then you just weld, okay, this gold wire to this aluminum pad, just like this, with the thermal melting, okay? And then if this aluminum is corroded, and aluminum is corroded only by the chlorine with the moisture, then this gold line is going to be detached from the pad, so that it's not going to work anymore. Now, this thing is important because it's related to the guarantee period of the product. You know, if you can find the defects in during the manufacturing, then it's not a big problem. But if you have to change the product after you sold them, then you're going to have a big damage. So you sometimes hear the news, the recalling of the automobiles and things like that. And that even the number of recalling is not that big. It is going to give the company a big damage if the recall happens. Now, this corrosion of the aluminum pad with the reaction, chemical reaction of chlorine somewhere from the environment will give you a very big effect. Okay? So you have to prevent this. How do you prevent this? All you have to do is you have to have a passivation layer. Corrosion. You have to have a good passivation layer so that you're going to prevent to have chlorine ions and the moistures. See, the chlorine ions, where you get the chlorine ions easily, you're going to have a sweat or human body. It contains the chlorine ions in there, and the moisture in the environment, in air, you're going to have a very good chance to have a chlorine. But if you get rid of this moisture completely, then chlorine itself is not going to react with the aluminum. So with a good passivation, you're going to have moistures in your device, and with a good cleaning, you're not going to have any contamination with the chlorines. Okay. So to prevent the corrosion, you are going to have a very clean room to manufacture the device, and you are going to have a very good passivation layer like a silicon nitride and so forth. And PR usually used for the passivation layer because it is easy, but the PR is not good enough. It's like a vinyl. The PR is not good enough to completely cut off the moisture. So these days, the nitride is the most common passivation layer. Now, the electromigration, that is a very important and there's a serious problem in the metallization. And in this explanation, you can see the metal lines is so narrow, and the thickness is about the angstrom size, like 1,000 angstrom or something. So in there, even though you are running very small amount of current, since this line is very thin and narrow, it is going to affect, it is going to show the electron migration. What is electron migration? Okay, 4 times 10 to the 5th or 2 times 10 to the 6th amps per square centimeter. It's going to flow in your VLSI devices. At home, usually 4,000, 4 times 10 to the 3. Okay, compared to that, you are under very severe conditions. Your VLSI devices is under very severe conditions, right? So you're going to have a very fast flow of electrons. That is the current. And you may see that there is an electron wind, okay? So in a metal lines, you're going to have aluminum ions like this, which is very sluggish. It's not moving at all. But if you have a DC current like this, at that high current density, even 100 or 1,000 times higher than the current at home, you're going to see the wind of electrons. Electrons are moving to is a one directional moving, and we call that wind. Okay, so field force, and this electron wind is physically react with the ions, but more seriously, it is going to have a coulombic force working on these ions, so that actually it works to move these ions. So the movement of the ions by electrons is electron migration. It's going to be called electron migration. So electron in the front of the electron migration, it's just the field, the force to make the ion migrate. Okay? So electron, if you have a movement of electrons, then no physical phenomenon happens associated with that. We just have electricity. That's all we have. But if you have a situation that the ions are moving, then we have a difference, change in the physical. In a physical sense, you know. So the lines can be broken if the ions is moving from one place to the other. Then at the other end, ion is accumulated, but in this end, we have a depletion of ions, something like that. Well, this electron migration can be used for purification. That is good. So if you have a molten ions, okay, and then you apply high field to that, then the impurities are going to be moved where there's a high electron field, so that you can purify or refining things like that. The bad thing, the failure, because ions is moving, so physical dimension is going to be changed. And one of the things is the failure. Okay, the Nernst-Einstein equation is related to the diffusion coefficient and activation energies, all that. And then it turned out the activation energy for the electron migration, aluminum is just 0.4 electron volts. If you have a low activation energies, then the electron migration can happen easily. Okay? Gold, 0.9, pretty high. We never get the electron migration in the gold lines. And if you add copper and you add the silicon, it's just for prevention of junction spiking, as we discussed number 1 there, then this is the typical line, metal lines, and it has the activation energy is 0.44 to 0.77. So 0.77 is a reasonable, close to the gold. So we can prevent electron migration to certain point with the addition of copper into this. Now, how much copper we should put in there? This electron migration really happens along the grain boundaries as well. Okay. The ions is moving with the electron wind, and that ions will find its road on the grain boundaries. So grain boundary is affecting the electron migration phenomenon. And we add the copper to prevent the electron migration, and we want to put the copper more than the solubility limit in this case. Solubility limit in this case. Why? Because if you have add the copper beyond the solubility limit, then we are going to have a precipitation, and this precipitation will happen on these triple points and grain boundaries rather than the intergrains, because this grain boundaries is unstable sites, so that it has a high potential to form a precipitation. So if you add the copper beyond the solubility limit into aluminum, then you're going to have a precipitation, and those precipitation is preferably formed at the grain boundaries, and those grain boundaries will block the ionic motion in the electron migration. Now this is one of the interesting results. This is temperature. So one over T, reciprocal temperature, so that it has a low temperature in this side and it has a high temperature in this side, and here the diffusion coefficients. And at low temperature, the grain boundaries diffusion is the only thing that can happen at low temperature. But if you move to the high temperature, then the intergrain diffusion can happen, because you have high enough energies, thermal energies. Okay, so in this experiment, at high temperatures, the diffusion coefficient we have represent the diffusion coefficient in the material. But as you move to the lower temperature, only diffusion along the grain boundaries will happen, so that the diffusion coefficient that we measure is very sensitive to the grain size. Okay, if you have a small grain size, then it means that you're going to have a large area, a grain boundary area. So you have a higher diffusion coefficient. So in this slope, as you decrease the size of grain boundaries, this line is going to move to upwards. Okay, but if you have a temperature, critical temperature more than critical temperature, then this grain boundaries effect is not going to see anymore. You can see only one diffusion coefficient, no matter what the grain size is. Okay, this is one of the experiments we can tell the grain size of your specimen. Now, if you have a uniform grain size in your metals, of course, there is a triple point which is related to the electron migration as a depletion or accumulation of atoms. And the grain size itself, the triple point is very much dependent on the grain size. If you have a large grain size, you have a large accumulation, large depletion, things like that, comparing to the small grain size. And this thing happens, A, C, D, it also happens on the B, where we have you are going to have ununiform grain size in your metals. Let's suppose you have a small grain size, and in the middle you have a large grain size, not uniform grain size in your metal lines. Then you're going to have serious electron migration effects in there. Okay? And that is the grain size effect. Okay, and then geometric effect also related to the electron migration. So in the electron migration, we're going to have two effects. One is the geometry effect. Geometry. And you just discussed about the grain boundary effect, right? Geometry effect. When you have a pad and you have a large size here, and then you have a metal lines. Okay. Now metallization consists of two things. One is the metal lines connecting each the transistors, and the pad, formation of the pad, which is going to work as a input and output base, right? So if you have a large area of aluminum and then you have a small metal lines connected to this, and this difference in the geometry, and if you have electron migration, then as you can see, the atoms are moving from here to here. Then at this point, you're going to have accumulation of aluminum ions, because you have many entrance and you have only one exit, narrow exit. But at the other end, you're going to have a voids, depletion of metal atoms and things like that. That is a geometric effect. Now let's see the effects of line width. That is a very interesting thing. You know, you decrease the metal lines from 2 microns, 1.5, 1.0, and 0.5. And as you can see, you decrease the metal lines, then this is a median time to failure, which means electron migration, how easy the electron migration can happen. Okay? And then as you decrease the lines, then the lifetime of the metal lines is going to decrease somewhat, decreasing. But if you decrease the 1.0, more than 1.0, then suddenly the lifetime is going to increase. Why is that? Because we are going to, if you decrease very much, then you're going to have a bamboo structure. We call this the bamboo structure. No triple point at all. So if you decrease the metal lines of thickness or width, not to have the triple points, then electron migration also can be prevented to a certain extent. That's a very interesting point, isn't it? Okay, finally, the thermal migration. Thermal migration is a temperature difference will give you the difference in the diffusion coefficient. So if you have let's suppose you have a temperature gradient, something like this. So at the center you have a highest temperature, but at the other end you are going to have a relatively lower temperature compared to the center. And this thing can happen in the VLSI if you have a different width of the metal lines. If you have a large area of the metal lines, then the heat is going to be dissipated into the air more than at the center if the heat comes from the silicon substrate. Okay? So relatively you have a lower temperature at both ends, and at the center you're going to have high temperature. And then you are going to have a temperature gradient like this, and at this slope of a temperature, then more ions. It's going to move toward the high temperature, but at this slope, less ions is going to move towards to this end. So at this part, you're going to have a hillock, while at this part, you are going to have a voice. So you're going to have a necking phenomenon. You're going to have a failure at this neck, okay? And you're going to have a hillocks, a lot of rough surfaces at this end. And we call that thermal migration. And this is the typical example. It's a simple example, but very powerful, very clever. Transmission optical microscope. It's just a microscope, normal optical microscope, okay? A thin gold film, and using the alternating current, which means you are not going to force for the ions to move one direction. So you just have an alternating current so that there is no directionality of your ions to move with the electric field, right? And it just creates a Joule heating so that this alternating current is going to make your sample, the gold in this case, warm or hot, whatever, okay? And then you are going to have this large pad, and you add this node, say, to dissipate the heat so that the temperature here is different from there and here, okay? Here and here, things like that, okay? And the center, and then towards the node. So in this case, after how many? It says with this nodes, both ends at 80 degrees centigrade, at the center is the 350 degrees centigrade. It's a big temperature difference, okay? And you can see with the optical microscope, the thinning of metal lines, okay, because of the thermal migration. And here, this part, the white part, the gold is going to move. It has a depletion, while you have accumulation in the dark side, okay? So that is the thermal migration. Electrotransport, electromigration, that is a unidirectional. It has a directionality depending on the field. And thermal transport, thermal migration is symmetrical. So that's the difference between the thermal migration and electromigration. Anyway, this thermal migration, thermal temperature gradient on your substrate is inevitable, because before you put the metal lines, your substrate is going to be on the contact side is the source and drains, where the heavily doped silicon, and the metal lines on top of the gate, that is silicon, polysilicon, not a single crystal silicon, and the metal lines which is running over the field oxide that is on top of the SiO2. And sometimes the metal lines, also one metal line, single metal line, is going to running over the silicon nitride, which is different from the silicon oxide. So your metal lines, one single lines, it may run on the silicon, undoped silicon, doped silicon, and polysilicon, SiO2, and silicon nitride, and even one of the metal lines. Okay, so it has to run all over different substrate, and then if you put your sample in the heating furnace, then all different areas shows a different temperature, even if you put your sample in one furnace, one temperature. So that the metal has to experience the temperature difference, and the thermal migration is inevitable. Okay? And especially when you have a product, you finish the product, and then during usage of the product, it creates a lot of heat. If you watch the TV for a long time, then you're going to heat up your TVs and even your smartphones. Okay, if you use a long time, the battery is going to give you a lot of heat. Okay, and so that the chips in your smartphones is going to be heated up so that this thermal migration can happen in your handphones, even your handphones. And if the failure happens after 1 month or 2 months of usage, then you have to return it. And you are going to have a new handphone. And the company who manufactured the handphone is going to bankrupt. Easily. So these metallization problems, all these problems is related to the reliability. And reliability is the key of the manufacturability. You can make it or you cannot make it. It all depends on the reliability, not just on the process itself. Okay? So metallization, in that respect, metallization is very important. As a final sessions, it has a data analysis. And if you look into the data analysis, there's 1, 2, 3, 4, 5 points has to be remembered. You have to notice there's the 5 points, and then you analyze the results. You cannot directly relate the measurements and the real affairs happening in your device, okay? Because all your experiments, there's 5 points has to be taken into account. Okay, well, in this lecture, we try to cover the introduction of the VLSI processes, and since we have discussed the topics in English, maybe it is difficult for you guys. Of course, it is difficult for me too, but you may have difficulties in understanding. But basically, everything is written on this book, so it's not a serious discussion, but it covers the introduction part. So if you guys are interested in one chapter or the one session or the one problems discussed in this textbook, you can find the literature related to that without much difficulties, because VLSI, now the Chinese can do it now, which means it's very common. It's not high tech anymore, right? So in that respect, this class has been interesting, and it's not going to be, it is not meant to be burden to you guys. Okay, we are going to have a final on the 1st of June, right? And it's going to be a 2-hour exam, but you can finish it within 1 hour if you like. And it's an open book. You can carry anything you can carry, even computers. You can carry the computers, no problem. All right? Any questions? I want to hear something in English of you guys. How come this class is so one-directional? How do you like this class? And at the first class, I told you that our lecture is uploaded in the YouTube. So if you want to review any lectures, you can search in the YouTube. I think this is the first time in our department. I think in Seoul National University, it doesn't have many YouTube lectures. Okay? What? Hey, say something.